Now that we have reviewed groups, axioms, examples, definitions, etc., let's focus in on the meat and potatoes of this, which is to look at Burnside and Polya. We're going to start with Burnside. Burnside is a way, essentially, for us to look at equivalence classes. Let's take a look at a square with tokens at each vertex, or essentially I'm saying you've got big circles on each vertex, and they're either black or white. So obviously the way that I've written these, all four are black at this point. My question is, how many ways can I color the vertices? Well, this guy can either be black or white, so that's two different ways. This guy has two different ways. This guy has two different ways, and this guy has two different ways. So that's 2 to the 4th, or 16 possibilities, because 2 times 2 times 2 times 2. So we're going to call that S, because that is essentially the sample space. I have 16 total possibilities. Now, I have listed for you all 16 of those possibilities so that you didn't have to write them out. So before you start reading all of this stuff over here, let's just take a look at the work that I've copied from your textbook. So I have a square where all of them are black. I've got a square where I've made the bottom left white, or I've made the top left white, or I've made the top right white, or I've made the bottom right white. So those are all of the configurations where I have 3 black and 1 white. And notice I've grouped them. We're going to talk about that group in just a moment, but for now let's keep plugging away. Now I've got 2 white, and now I've chosen the 2 bottom, or the bottom and the left top, or the top left, top right, or the top right, bottom right. So that's 2 white, 2 black. And I've grouped those together, but I didn't group them with this set, which is also 2 black, 2 white. But if you'll notice, the 2 black and 2 white are catty-corner from one another in this example. And so we'll talk about why those are grouped together in a little bit. Then we look at, now I've got essentially the same thing I had up here, but now I've got 3 white, 1 black, so sort of the opposite. But again, notice the black one's top left, top right, bottom left, and then of course they're all white, which is my very last configuration. Now what I wanted to do then is to say, let's group like things together. And when I say like things, I mean that if I can find a configuration by rotating or reflecting, then it's not distinct. So for instance, if I took this guy right here and I just rotated it to the right, then I get this guy. And if I rotated this guy to the right, then I get this guy. And if I rotated this guy to the right, then I get this guy. So these are all essentially the same because I can get the same thing by a rotation or a reflection. So I've grouped these together. This guy I didn't group with anything else because all 4 are black and nothing else changes. Now let's look at the 2 where the 2 blacks are side by side and the 2 whites are side by side. Again, by rotating to the right, I can go from one of these to the next of these. So that's why I grouped all of those together. And the reason that I didn't group these with these is because I can't rotate this or reflect this and get one of these. So even though it's still 2 black, 2 white, these are a different class, a different set, and we're calling these sets orbits or equivalence classes. So this guy is separate because I've got catty corners, and then kind of like this guy up here, I've got these guys down here, which is 2 whites, 2 blacks, 3 whites, 1 black, and again, just by rotating one to the right, I can end up with the next configuration. And then of course the last one is all white, and just like all black, there's nothing else like it because all 4 are exactly the same. So looking at this, again, the long way, I have noticed that I have 6 equivalence classes, or 6 orbits. And again, that is found just by the long way, plug and chug. Let's look again at these symmetries of a square. Remember, we had rotational symmetries and reflectional symmetries. This is just a recap of the rotational symmetries. The permutation groups are not as important in this particular video, but when we talk about polio, we'll be looking at this in a little bit more detail. But for now, essentially, we're saying, here's my starting position, and notice I've just gone clockwise instead. It really doesn't matter if we go clockwise or counterclockwise. So if I went clockwise, then 90 degrees, 1 moves to 2, 2 moves to 3, 3 moves to 4, 4 moves to 1. So this is my result. If I go clockwise 180, then it's 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. And again, we should recognize this from 16.1 video that you should have just watched. And then again, 270 means I'm going 270 degrees, or 3 pi over 2, and I end up with the new result of 1432. If I look at the reflections, then I have the horizontal reflection, the vertical reflection, and again, I've got my permutation groups down here. I have the diagonal through vertices 2 and 4, and then I have the diagonal through vertices 1 and 3, and that's all of my reflectional symmetries. So again, G is just the group of motions, the group of reflections and rotations that I can use. Pi 0, pi 1, pi 2, pi 3, and then R1, R2, R3, R4. Now what I want to do is I want to take a look at each of the 16 that we had looked at before, and I want to determine the number of stabilizers. Stabilizers means what's going to give me the exact same coloration. So which one of these G's is going to give me the exact same thing? So if I rotated this 0 degrees, what would happen? I would end up with another square that had black on each corner, right? So this is a stabilizer because all of the colors remain the same. Pi over 1, because that is a 90 degree, not pi over 1, sorry, pi sub 1, which is essentially a 90 degree, or pi over 2 rotation. Still, I'm going to have this square with 4 black corners, and really any of the rotations are. So all of these work for the rotations. For the reflections, same thing. Whether I reflect this way or this way or this way or this way, no matter what, I'm going to end up with a square with 4 black corners. So for my first configuration, every single element in the group would result in the same coloring. So I get 0, 1, or pi 0, pi 1, pi 2, pi 3, R1, R2, R3, R4. Now if I continue that process and I look at C2, and again I'm looking for the number of stabilizers. So if I don't rotate at all, I get the exact same thing. If I do any other rotation, it's not going to work because this white guy is going to end up somewhere else. So the only way I can end up back here is if I go 360 degrees or don't rotate at all. So notice I've written pi 0. In terms of reflections, this doesn't work, this doesn't work, this doesn't work, but the one I have marked in pink does work, which is we're calling R3. So I continued that for each of these, and again, if you'll notice, if I don't rotate at all, or if I use one of the diagonal rotations, depending on which original configuration I have. So essentially I have two different ways to do it, times 4 because there's 4 things. Then I look at my next group. And again, rotations don't really work for me unless I'm rotating not at all. And then I just have one reflection, and again that changes depending on which one I'm looking at. For C10, I'm looking at a rotation of 0 or a rotation of 180 degrees because white goes to white and white goes to white and then black goes to black and black goes to black. So the rotation of 180 degrees would work. So notice that's why I have not rotating at all, or a rotation of 180. And then again, this guy wouldn't work because black would go to white and white would go to black, and same thing this way would not work. But my two diagonals work because it would fix black to black and then white would reflect to white, or it would fix white to white and black would reflect to black. So those two reflections work. Same thing for C11. Moving on, and again that means there's 4 of them times 2 because there's 10 and 11 are both in there. For 12, again, I'm looking for anything where my configuration would remain the same, so not rotating at all, or as you can see, I've marked the reflections that will in fact work. And then last one, looking at C16. C16 is very much like C1 because all 4 vertices are the same, so I've got a lot more freedom because I can rotate 90 and still have white, 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 rotate 180, rotate 270, etc., or do any of my reflections and I still end up with a bunch of whites. So this brings us to Burnside's theorem, and Burnside's theorem essentially is a way for us to determine the number of equivalence classes or orbits. That's what we're looking for. To determine that, and obviously we already know the answer here is 6 because we did it the long way. And you might think, wait a minute, that other way was the short way? Well, I'm going to show you a little shorter way to do what we just did. I just wanted to make sure you had the visual in your head before we did it together. So essentially they're saying take 1 divided by the size of G. So the size of, in this case, 8. And remember, G was our group of symmetries, which was pi 0, pi 1, pi 2, pi 3, R1, R2, R3, R4. That's why there were 8, because there were 8 different rotations and reflections that we were using. So that's why we're using 8 here. Then it's saying, and essentially all we're doing is finding an average. We're finding an average because we're taking 1 divided by the number of different symmetries. And then essentially what we're doing here is we're adding up the number of elements that stay fixed. Okay, which is what we just did on that other page. So if you'll notice, I've just sort of recopied them here. In S1 we had 8, all 8 of them stayed fixed. 2 through 5, which there were 4 of those, had 2 elements that stayed fixed, so notice I just took 4 times 2. 6 through 9, remember they were all in the same equivalence class, and we had 2 elements that kept everything fixed, so again 4 times 2. 10 and 11, there's 2 of those, so 2 times 4. Here 12, 13, 14, 15, 4 times 2, and then just one of them had all 8. So again, if I add all of these up, I get 1/8 times 48, and I get 6. Now, did I already know the answer was 6? Yes, I did, but this is going to be an easier way. So, thinking of what we just did, and knowing that I really don't want to draw out all of my configurations and draw the lines through them all the time, let me show you a little bit better way. We're still going to use Burnside's, but it's going to be a little bit easier to come up with the values here. So let's take a look. Organizing this in a different way, and then this is the way that makes the most sense to me because I'm lazy. I don't want to have to draw all of those pictures. I don't want to have to do a lot of work. I just want to be able to find the answer quickly. So the first thing you have to know how to do is, of course, know the symmetries, and we've already been through those, so I'm not going to go through those again. We've got 0, 90, 180, 270, and then we have the reflections, horizontal, vertical, each diagonal. What I want to do is I'm going to look at the stabilizers. So I'm going to try to fill in this table. That was a horrible arrow. fill in this table as we go with how many, and I'm going to focus on the fact that we have two colors. We have white or we have black. So if you'll recall, those were the two colors, and it doesn't matter that it's white and black. It matters that there are two of them. So let's take a look. If I don't rotate anything at all, 0 degrees, how many colors can this vertex be? Well, it can be 2. How many can this be? It can be 2. It can be anything, because I'm not moving it at all, so nothing has to line up or match up, so I get 2 to the 4th. That's what's stabilized. Everything, which was my original 2 to the 4th. Great. Let's take a look at 90. And hopefully this will make sense. This guy, and I'm just always going to start with the top left just for fun. This guy can be whatever color I want. So any of the two colors that I'm choosing from. But if, let's say, I chose this one to be white, then this guy would have to be white, and this guy would have to be white, and this guy would have to be white. If I chose it to instead be black, in order for the configuration to remain the same and still be rotating 90 degrees, then this would have to be black, and this would have to be black, and this would have to be black. So I only have 2 times 1 times 1 times 1, or 2 colors, as opposed to 2 to the 4th, where I could use any color I wanted on my last one. For 180, sorry, there's going to be a lot of drawing and erasing, which is the beauty of digital ink right here. So for 180 degrees, I'm saying this guy is going to map over here, which means these two have to be the same. So I can have two colors here, but this guy has to be whatever I chose for the top left. And then this guy can be two colors, but this guy has to be whatever I chose for the top right. So that's where I came up with 2 squared. Hopefully you're following this. Then I'm going to look at the next one, which is 270, which is really just like 90. We're just going in the opposite direction, so that's 2. So I'm done with my rotation. 2 to the 4th plus 2 plus 2 squared plus 2. Now let's look at reflections. If I'm looking at horizontal. For horizontal, this guy can be whatever color I want, but because it's going to flip down here, this guy can only be whatever color I chose for the top left. This guy can be whatever color I want, but this guy can only be whatever I chose for the top right. So 2 squared. Same thing for vertical. This guy can be whatever I want, but this guy has to be whatever this was so that they match up. This guy can be whatever I want, but this guy has to be the same. So that's 2 squared again. Then let's look at the diagonal 1. Diagonal 1 says this guy can be whatever I want because it's actually not going to move. And this guy can be whatever I want because it's not going to move. This guy can be whatever I want, but this guy has to be the same as whatever I choose up here in order for that to fold over and be the same configuration. So that's 2 to the 3rd. And as you can imagine, that's what's going to happen going in the other direction as well. If I go this way, this can be whatever I want, as can this, but this guy has to match up to whatever color I choose down here, 2 to the 3rd. So that's where I get the second set of 4, 2 squared, 2 squared, 2 to the 3rd, 2 to the 3rd. That gives me 1/8 times 48. That gives me 6, which is the same answer I had before. Let's take a look now at the chessboard problem, which will be similar. Now it's still a square, so we still have G exactly the same. But S, which remember that was the sample size, is now 2 to the 16th. So where did I come up with that? Well, there are 16 squares, and each square can have 2 colors. Again, we're just focusing on black and white. So 2 colors times 2, etc. 16 times for our 16 squares. So that's where we get 2 to the 16th. Now let's look at this one in terms of cycles. How many elements are fixed by not doing anything? Well, obviously all of them. What about pi over 1, or I'm sorry, pi sub 1, which is 90 degrees? Well, if you'll notice, I've sort of used some color coding here and said, all right, well, if this can be whatever color I want, that's my first one. This has to be the same color, this has to be the same color, etc. So I'm going to keep those pink so as to not confuse. And then I've got my blues, so this can be whatever color I want, but then this guy has to be the same, and this guy has to be the same, and this guy has to be the same, etc., etc. So the only way to make this happen is with 4. So I've got essentially the 4 in the top left corner that I can make whatever I want. And then from there, everything else is already set based on what I set for 1, 2, 3, and 4. So that would be 2 to the 4th, and that's for 90 degrees, and it would be the same for 270 degrees. So if you'll notice, I've got pi 1 is 2 to the 4th, and pi 3 is 2 to the 4th. And remember, I didn't write that down here, but pi 0 was 2 to the 16th. So that's what I have so far. So the only rotation I haven't looked at yet is pi 2, which is of course 180 degrees. So looking at 180 degrees, again, what I'm really looking at is I can choose anything I want for any of the 8 spaces on the top half of the board or the bottom half, it doesn't matter. And by going 180 degrees, essentially what I'm saying is whatever I choose here, I have to choose here. Whatever I choose for 2 has to also go here. Whatever I choose here also has to go here. And again, that's so that I can end up with the exact same configuration. So there's 8 choices, 2 to the 8th colors I can choose. The others are fixed. So pi 2 is 2 to the 8th. Now let's look at reflections. If I had a horizontal reflection, which would be the same as a vertical reflection, same concept. Again, on half of the board, 8 spaces, I get to choose whatever color I want. The other half of the board is going to be whatever I have chosen for the first half of the board, so I don't really have a choice there. So that's 2 to the 8th because I'm choosing 8 spaces. And then for across a diagonal, this one's a little bit different. So both a horizontal and vertical reflection were 2 to the 8th. This one, whatever I choose for a half of the board diagonally, as well as what's on the diagonal, because those obviously will stay fixed. Essentially, I have 10 choices to make, so 2 to the 10th. The other ones are just going to be whatever got reflected across the line. So that's for both 3 and for 4. So what's my final solution? Well, essentially, I'm just going to add those up. This was for pi 0, was 2 to the 16th. Pi 1 was 2 to the 4th. Pi 2 was 2 to the 8th. Pi 3 was 2 to the 4th. R1 was 2 to the 8th. R2 was 2 to the 8th. R3 was 2 to the 10th. And R4 was 2 to the 10th. Add all of those up, and I get 8,548. So that's how many equivalence classes, or remember, these are also called orbits. And that's what we're using Burnside's theorem to determine, is orbits. Now, the good news is, what if I said I can use black or white or green or yellow? Would I have to do all of my work again? No. This is 4 different colors, right? So all of these base 2s would change to base 4s, but essentially my work is done. One last question for you to try. This one is an equilateral triangle. So we haven't talked about G, the set of G for this, but I'm confident you can figure it out. Obviously, I've given you the reflections. You need to look at the rotations and how many we would have. And this one I've given you 4 colors. So how many ways can I color the vertices? So come up with G, which is all the reflections and rotations, and then make sure you come up with S, which is the sample space. Again, that would be using this number of 4. And then go ahead and determine the number of equivalence classes using Burnside's theorem. When you're ready, press play to see how you did. So hopefully you came up with the fact that because it's a triangle, I can go not at all, I can go 120 degrees, I can go 240 degrees, I can go 360, which is back to 0. So there's 3 rotations, and then reflections. Obviously I cheated a little bit and gave you those already, R1, R2, R3. So the size of G, I'm going to move over S, the size of G is 6. My question is now, what is the size of S? Well, if I have 3 vertices, and each of them can be 4 colors, this can be 4, this can be 4, this can be 4, so that's 4 to the third. 4 to the third is 64. Oops, 64. So now what do I need to do? Well, now I need to start doing my work. And my work is to determine if I don't rotate at all, what stays fixed. So if I don't rotate at all, everything can be whatever color I want, all 3 vertices. If I rotate 120, well, whatever I choose here, this can be any color I want. This has to be the same color, this has to be the same color, so it's really just 4 different colors. If I look at 240 degrees, that means this guy's going all the way here, so this guy can be 4 colors, but then again this has to be whatever I chose before. This is going to go all the way over here, so I really only have 1 color here, and this is going back here, so I just have the 4 times 1 times 1, which is 4. Okay, that's this guy. Now I'm going to look at reflections. That was all 3 of these. Now let's look at a reflection. Reflection 1 means this guy can be whatever I want. This guy can be whatever I want, but this guy has going to flip over here, so that has to be the same one. So 4 squared. Same thing's going to happen for really all of the the reflections, because the one that is fixed will be the one that the line goes through, and then the other one, you can have one that you choose and the other one is fixed based on whatever you chose for the second vertex. So 4 squared, 4 squared, that gives me 1/6 times 120, and again the 6 came from here, and that gives me 20 equivalence classes.